Hello everyone. For those that we have not met before, I am Utpal Bora. I am a PhD student at Indian Institute of Technology, Hyderabad, and I work in mostly in compilers. And yeah, I am about to graduate. Yeah, that's all. I think I like to attend this not only meetings, like informal meetings and presentations where you can learn from different people. And so like last time I joined and I volunteered to present, so yeah, here I am to present what I'm working on. And hopefully you will also find some use to whatever I'm working on. That's the main motive. So then shall we start? Okay, let me share the entire screen. Is it visible?
Oh, yes, it is. Yeah. Wow.
All right. So I'll try to like focus mostly on the learning aspect and not in the theoretical aspect or the, the background for paper or like formal things. I would prefer a generic overview of the things in this talk. And if you have any questions, raise your hand and ask immediately. Maybe that is, I think, better. I would prefer that everyone is at the same page on this.
Oh,
All right.
yeah, yes. If you are comfortable with it, definitely. And in case, I'll say that you focus on the talk, and I'll interrupt you when someone will raise their hand. Yeah.
Yes, please. Thank you. So I think like it is better to ask questions
Sure.
immediately so that if like others have any doubt and they are not asking, it will be clear to everyone. All right.
Yes.
Okay then. So today I'll talk about data race detection in OpenMP programs, and for this I am using the LLVM framework, which most of us are using and very familiar with. So in this talk, first I will introduce you to what OpenMP is. Maybe most of you are familiar with. Still, I'll give a brief introduction to what OpenMP provides for C, C++ and Fortran programs. And I'll talk about the main problem, that is data races. And I'll provide some details of the work that we are doing here at IIT Hyderabad in detecting data races. And finally, I'll show some comparative results with the state-of-the-art tools. And if time permits, I'll show some hands-on with some examples. All right. So if you have any questions, then immediately you can ask. Okay. So what OpenMP is like for most of us, we must be using the in the standard what do you call the libraries that are provided in the programming languages for multi-threaded programming. But there's another API called OpenMP, Open Multiprocessing, where which can be used to achieve parallel programming on a shared memory system. So there are multiple benefits of using OpenMP. So here I'll list them. Like in OpenMP, we can do SPMD kind of programming that we generally do for GPUs. I hope everyone is familiar with this programming model. And then for SIMD programming model as well, OpenMP provides pragmas, and then we can do divide and conquer operations using task in OpenMP, so that the designing of design and conquer algorithms becomes much simpler using this OpenMP task. And OpenMP provides a data sharing environment or data environment which is used to provide the consistency of the shared memory. among different threads. And since it is a parallel processing framework, we need to have mutual exclusion, atomicity, and implicit and explicit synchronization. And most importantly, OpenMP is getting popularity because it's like across different architecture, it is portable. If you take CPU, GPU, FPGAs, you name like Intel, then and any other PowerPC, any other vendor you talk about it, OpenMP is portable. You write once and you can port the same application everywhere. So that is the big plus point for OpenMP programs. So let us see how the execution environment works for OpenMP. Generally, the OpenMP programs are like not always, but generally they are they are recognized by the parallel constructs. So in a sequential program, we will have a pragma, which will define that a section of a program is parallel. So in this example, in listing 1, we have a C program from line 4 to line 8. Then surrounding that, we have defined a pragma, which is a parallel construct. So this construct is specific to OpenMP, and it states that the body of the construct will be executed by different threads simultaneously. So here, in a pragma, we can have different parameters like num threads. We call them as clause. Okay, and here num threads 3 represents that we need 3 threads, 3 runtime threads to be executing this parallel construct, and the sequential body of the program will be executed accordingly. So how this execution happens, if you look at figure 1, so if it was a sequential program, thread 1 will be like just there will be one thread which will be executing the whole for loop sequentially, like iteration 0, 1, 2, 3, 4, all the way to the number of iterations, the trip count we have for the for loop. But for the parallel program, since we defined that we need 3 threads, we will have 3 different threads executing the body. So one very important thing to note here is that the work done by the different threads in this parallel construct will be redundant. As you can see that thread 1 also executes from iteration 0, thread 2 also executes from iteration 0, so on and so forth. All the threads participating in a parallel construct will repeatedly work the same task. And all the threads in a parallel region are called as a team. Just remember that. And there another very common construct which is called work sharing construct or work sharing for loop. Here, as shown in listing 3, we have a pragma parallel for, then a schedule. This schedule is basically a method of executing the threads at runtime, executing the code at runtime, and then number of threads will define as we have discussed before. So one difference between this loop or this pragma and the previous one is that since this is a work sharing loop, the work will not be repeated by all the threads. As you can see, thread 1, thread 2 and thread 3 will combinedly work the whole loop, and the iterations will be divided among them. So iteration thread 1 works on iteration 0, 1, 2, 3, 4, and then next next chunk of iterations will be done by thread 2, and so on and so forth. So the execution stops after iteration 14, after I equal to 14. Right? Similarly, if we have like this is a similar example, but with a lesser trip count, which is 11. So in this example, so what OpenMP will do is it will try to assign equal amount of work to everyone. So first it assigns like first 4 iterations to thread 1, next 4 iterations to thread 2, and last 3 iterations to thread 3. Even though like there are no work to be done for thread 3, after iteration I equal to 10, it will have to wait for the other threads in the team. So it is very important to remember that this kind of parallel for construct will have an implicit barrier at line 8. So everyone has to wait, all the threads have to wait at line 8 so that other threads in the team finish their work. They cannot proceed forward, right? So I hope you understand, like you are getting the gist of the scheduling. So there's a slight difference between this schedule at listing 4 and this schedule at listing 5, where we have provided a number which is called the chunk size for the static schedule. So here what static means is that at compile time itself, we know which thread will execute which iterations of the loop. So it can be, there are different types of schedules like dynamic, runtime, auto, and guided. All the other schedules will delegate the task of scheduling to the runtime, but in static we know which thread executes which iterations. And when we provide this chunk as 1, here the runtime, the compiler will assign alternative iterations to each thread, like thread 1 will get iteration 0, thread 2 will get iteration 1, thread 3 will get iteration 2, so on and so forth. So it's like in a round robin fashion, 0, 1, 2, 3, 4, 5, all the way to 12, 13, 14. So if you go back to this example where there is no chunk, here the huge chunk, contiguous chunk is assigned to thread 1. Next chunk is assigned to thread 2, right? In this example, it is happening with the number of chunks that we have provided. If we increase this amount to 4, now 4 consecutive iterations will be given to one thread. Like thread 1 will get 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, since there are only 15, the loop goes only to 15, so there's no work to be done for thread 2 and 3. Thread 1 will continue with iteration 12, 13, 14, 15. So these two threads will have to wait for thread 1, right? So this is the main idea behind the work sharing loop. So if we look at figure 7 for the example at listing 7, where we have a pragma at the outer loop, right? So in this example, when we say that parallel for is associated with the first loop, right? So because we have not provided any more information, that means this parallel for will distribute the first loop. Even though there are multiple loops in the loop nest, only first loop iterations will be divided among the threads. All right, so the division occurs as shown in figure 7, where in the I, because the outer loop is I, the I dimension iteration will be chunked statically with 4 iterations at a time. And thread 1 will get these 4 iterations, thread 2 will get these 4 iterations, so on and so forth. And since the inner loop is not associated with the parallel for construct, it will not be divided at all, right? So what happens if we put this construct in the second loop? In this example, the inner loop is associated with the for construct. That means this iteration will be divided. So which will happen in this fashion. The first 4 will be assigned to thread 1, next 4 will be next 4 iteration of the j dimension will be assigned to schedule thread 2, so on and so forth. Right, so this will happen in a round robin fashion, 1, 2, 3, then again 1 will start, right? Thread 1 will get the next iteration. All right, so this is the main idea behind the work sharing and the parallel constructs. So those are the most important constructs that, as you can see. Let me go through, maybe I'll cover this little later. So okay, first I'll introduce vectorization and parallelization. Right. I hope everyone is aware of this. But in this example, can anyone tell me if it is possible to vectorize this example? You can just ignore the trip count. You can pump up this trip count. Maybe this vectorization might not be that much cost efficient, but yeah. Anyone?
No, I don't think, because there is a dependence between B of INJ and B of IJ minus 4, right?
Yes, you are right. Ideally, that because of this dependence, we will not be able to do vectorization. But like, what about the iterations from 1 1 to 1 3, 1 1, or maybe 0 0 0 1, 0 2 0 3? How about something like this? Is it allowed?
Okay, yeah, I think so. Because you calculated the four
At a time.
values that you need, and then you can use that for the other iterations, right?
Right. So this is only possible when we have a sequential thread. Like one thread works and then waits for the next vector instruction to complete the next 4 chunk, right? Okay. So what about parallelization? Can we parallelize the same example? Yes, I have introduced this parallel for construct. Can we just say that please schedule 4 iterations at a time? So the division of iterations will be like thread 1 will get 0, 4, 0, 5, 0, 6, and 0, 7. Then thread 2 will get 0, 8, 0, 9, 0, 10, 0, 11. Is it possible? So remember that these 3 threads are independent of each other and they can execute at their own pace. So what can happen is that this before thread 1 completes 0, 7, thread 2 can start executing its 0, 8 instead. So this is an incorrect parallelization basically. So there will be there will be incorrect output because of the ordering, right? So can we use barriers? So what if we say that, okay, first thread will do this, all the threads will, thread 1, thread 2, thread 3 performs the first iterations 0, 4, then 0, 8, 0, 12, and all of them wait on a barrier. So this is the barrier that is represented by the dotted line. All the 3 threads completes their first iteration, and then they will signal each other that we can go to the next iteration. Then executes 0, 5, 0, 9, 0, 13. Is it possible like this? Theoretically speaking, we are actually preserving the dependencies, right?
Yeah, that's right. Once you have a barrier, then the results would be correct.
Yes, exactly. But the thing is, this is not allowed in OpenMP. So wherever there is a work sharing construct, we cannot put a barrier. So for all the work sharing constructs in OpenMP, we cannot put a barrier inside it, right? So this is not allowed basically, right? How do we overcome this? What we can do is we can just parallelize the outer loop, right? And don't care about the inner loop. Is it clear to everyone that the outer loop do not have any dependence? So if we look at the iteration domain that each of them gets, so thread 1 gets 0, 4. Yeah, thread 1 gets 0, 4, then 0, 5, 0, 6, 0, 7, right? All the way. So basically I is not changing for thread 1. thread 2 gets 4 I equal to 4 constantly and j changes, right? So basically one thread is not like two threads are not writing to the same column, same row, sorry, right? So I equal to 0 is specifically assigned to thread 1 here, right? B of I0 j varies, so that will be written only by thread 1 and also read by thread 1. So that means if we read and write in the same thread, there is no problem in it because everything will be sequential, right? So there is no conflict. So all these things are happening sequentially in one thread, right? Now, if we consider like, can we do better? We can actually do better by enabling vectorization as well. That we can do using the SIMD construct, and we can restrict how many like iterations at a time we can see, right? So in this example, so we can actually parallelize the outer loop and vectorize the inner loop, right? So at one instance or one iteration of the thread 1, we will execute 0, 4 to 0, 7 in a vectored fashion, right? Similarly, for the thread 2, it will work on a different row of the array, and thread 3 will also get a different row in the array, right? So there is no conflict. This is how we use OpenMP to properly parallelize and vectorize and some examples. All right, so like, what are the problems we can have here? I'll quickly explain the data races. Like, as we have seen that it is important to preserve the dependencies to do vectorization and to parallelize them, right? What happens if we do not preserve the dependencies? So we can actually encounter some data races. What is a data race? A data race is a operation when two threads are simultaneously accessing the same memory location and there is no order to the memory accesses. So both of the threads are allowed to access the memory location in any order, and one of them should be right, because only right changes the contents of the memory, right? And also there should not be any mutual exclusion mechanism. Mutual exclusion can be achieved by like critical section or atomic operations, right? So, or locks. If we have a lock, we like, even though there are two threads trying to access the same memory location, if we have a lock, that lock will protect the operation. So unless the first thread completes each operation, the other thread cannot execute simultaneously. So that way we do not have a simultaneous access and there is no data race. So to have a data race, three things should be there. One should like, one operation should be a write operation, and there should not be any order, and there should not be mutual exclusion, right? So we will see some of the common cases that we commonly encounter in OpenMP programs. So I have categorized it here. So the first category is missing data sharing clauses. Okay, here I'll first introduce the data sharing clauses in OpenMP. Since OpenMP provides a data environment, what it does is like, it provides some clause with which we can say that a particular variable in the program is shared among all the threads, or it is private to each thread, or it is a reduction operation, or it is maybe linear variable which is specific to OpenMP. Here in example, here in this example in listing 14, as highlighted, the private clause marks the variables temp, I, and j as private. Okay, so temp, I, and j are private, and here there are other variables like len, u, and sum. So they are not marked as private. By default, OpenMP considers them as shared variables, right? So all the threads will access the same memory location. There is no like thread specific memory allocation for these variables. So out of this len, u, and sum, only some variable is being written, right? So in this case, there is a read and write operation to the variable sum at line 6, right? Since we do not have did not mark the sum variable as shared or as private or reduction, so in this case we will end up like writing to the same memory from different threads, right? So all the threads that are participating in this parallel construct will write to the same sum. So it will ultimately corrupt the data. Okay, so one solution is to mark this variable sum as shared. Sorry, in this case, this is the reduction variable. So one solution would be to make it as reduction, or another solution would be to put a lock just outside so that this operation is protected by locks or mutual exclusion, right? So there can be data races because of the loop carried dependencies. So this is a very common practice to have loop carried dependencies in application. Most of the applications or for loops will have dependencies or loop carried dependence. So what is a loop carried dependence? So loop carried dependence is a dependence which is across two iterations of the loop, right? We can have there can be dependencies within one iteration of the loop, but there can also be dependencies across the iterations of the loop, right? Multiple iterations. So in this example, in listing 15, because of the dependence from Bij to Bij minus 1, there will be a dependence from iteration j equal to 0 to iteration j equal to j minus 1, right? Previous iteration. So this is called loop carried dependence. So who is carrying this dependence? We call like whenever there is a dependence in a loop nest, we call that one of the loops will be carrying the dependence, right? So in this example, the inner loop is carrying the dependence, while the outer loop is parallel. So there is no dependence on the iteration of the outer loop because of these two memory accesses. Right? So when we try to parallelize a program which is a loop carried dependence on that particular dimension, in this case we are trying to parallelize loop at line 3 by using the pragma at line 2, but loop at line 3 has a dependence, so this will violate the dependencies and will result in data races, right? And there can be SIMD races. So SIMD races are similar to loop carried dependencies. We will have SIMD races only when we have loop carried dependence. So this like this is a special case of loop carried dependence. But the important thing to note is that while for this OpenMP parallel for construct, we will be executing by different threads. SIMD construct can be executed by a single thread, right? So there can be like data errors within a single thread as well. We need not have two threads to have incorrect result, right? And synchronization issue is very common. I think it is the most common problem in parallel programs. In this example,
sorry to
yeah.
interrupt. In the previous slide, you showed an example for SIMD, right?
Yes.
So that way compiler can figure out, I believe you can unroll this loop once, and you can get, and then can you do this in SIMD? Is it possible?
I guess not. Are you talking
Okay.
about loop peeling and then doing that?
Uh,
So even if we unroll it, basically
okay.
we will
Okay.
have the
Yeah.
dependencies, right?
Okay. Okay. Yeah. I'm sorry.
So no, it's fine. I think yeah. So even if we unroll it, like I should have covered the legality, the vectorization and parallelization legality. I will cover that slide later because that is not very important. So in that slide, I have covered when it is legal to vectorize and when it is not. So there are different methods or the different types of accesses or dependencies, like lexically forward, lexically backward. I will come to that slide later. Right? So in this example, at listing 17, so here at line number 4, we have a for loop. So this is a word sharing for loop that we have seen before. So one thing what we can do is whenever there's a parallel construct and inside it there is a for construct or Openmp for construct and no other construct. So we can, if this single construct was not there and the construct at line number 8 was not there. So if the parallel construct has only the only the Openmp for loop inside it, we can merge them. We can club them together, and we can call it pragma OMP parallel for. But if we have any other construct in the parallel region, we cannot merge them, right? So this is the first part is line 4 to 6 is the word sharing loop, right? And at line 7 and 8 we have a single construct. So what single construct says is that only one thread can execute it. All the other threads will not execute this construct. Whoever comes first inside this region will execute it. All the other threads will bypass it, right? So I also have mentioned before that a word sharing loop will have a barrier. That means, like if this no wait clause was not there, there would have been a barrier after line 6, right? So all the threads after executing this for loop repetitively, it would have to, they would have to wait at line 6 for the other threads to complete their share of the work, and they can proceed forward only when all the threads finishes their share and reaches the barrier. But if we provide no wait, that means the barrier is no longer there. So among the threads in this parallel construct, so among the threads in the team, whoever finishes first, they can proceed and start executing the thread at line 7 and 8. Right? So now what happens is that while some threads are executing this A of I, one thread can come and execute A of 9. Right? So there can be a data race from A of I to A of 9, line 6 to line 8. Right? Such cases are very difficult to detect, and like because it is a specific array access, so it will not happen for multiple array elements. It will happen only for one particular element. So such cases are very difficult to determine, detect, and reproduce. So like we will have to run the application multiple times to detect. And one more category is like control flow dependence. So whenever we have a control flow divergence, look, there's a control flow and some shared variable is written based on the data at runtime. There also we can have a data race. In this example, like whenever we have like threads more than more than 2 threads, I think there might be data race. Right? So 2 threads can write to the same memory location. So it is a very simple example, but we can have such cases because of the control flow dependence, right? So let us see how we tackle some of these problems in our work. So we have proposed a new tool which is LLOV. This is a LLVM based tool, so we have named it LLVM Openmp Verifier, which is language agnostic, and it is we do the checking at compile time itself. And since it is LLVM IR based, we can target all the languages that supports Openmp, Fortran, C, and C++. and we use the polyhedral framework poly to use to compute the dependencies for explicitly parallel programs. And we can conservatively state that some programs are data race free. This is specific, this can be inferred by static analysis tools only. So dynamic analysis tools cannot claim that a program is data race free, because a dynamic analysis tool will always provide you information for a particular set of parameters. So it cannot explore all the set of parameters. While static analysis has the advantage that if it is sound, it can specifically say that for some cases it is data race free. And yeah, so we can generate task graphs as well to visualize the programs. And yeah, so here is a high level flow diagram for our work. We can handle source code in C, C++, and Fortran, right? So for C, C++, we use Clang frontend, and for Fortran we use Flang. And first we compile them to LLVM IR. Since LLVM IR is sequential, first we need to like accumulate the information or reconstruct the Openmp information from the sequential IR, right? So the first step is collection of Openmp information, which we represent in a in-memory representation, and that representation is used by the actual verifier, right? So the actual verifier uses two things: alias analysis and the polyhedral engine. So we use modref analysis of LLVM to say if there is any race in a program. So this alias analysis checks are very conservative. On the other hand, the main race detection algorithm is based on the polyhedral framework poly, which works on this pragmas, and we analyze only the parallel section of the code that has been marked parallel by the Openmp pragmas. So if any races are detected, we generate race warnings. So first, what we do is, like for the example code here, we since the LLVM IR is sequential, which we will then represent in a in-memory representation, which will have like some variables like private. So these variables are marked as private, and shared variables, then first private variables, so on and so forth. And these constructs can have child constructs or child directives, which we represent in the in-memory representation as child directives. So this is based on a BNF grammar. Here, top level thing is a directive, which will always have a directive type, an optional schedule, and the list of variables like private, shared, and all, and then child directives. And the directive type can be any of the OpenMP standard directives, such as parallel, for sending, single, master. So the variables will have a variable type. So basically, this variable type is one of the data sharing types: private, first private, shared, reduction, and thread private, and yeah, other information as well. So we model them and use this in-memory representation to detect data races. So we do not target a sequential code. We know that sequential program will not result in data races because we need at least two threads to have a data race. And then we use the polyhedral representation to model these programs. Okay, let us take an example and see how we model them. For this example, as shown here, we have a parallel for construct in a 2D loop nest, and there is a statement which is marked as S0, right? And as we can see, there's a dependence from Dij to Dij minus 1. Okay? So first, what we will do is, we will, in polyhedral model, we will construct the iteration domain. So iteration domain will be computed from the loop iterations, like loop indices. So I equal to 0, I less than m, and for the j variable as well, right? And then we model the memory accesses. So we model the memory accesses for a statement as access maps. So how do we map is that for each read operation or write operation, we will have a map from which iteration that for which iteration the particular memory accesses was performed. So as you can see, for the access map A, for the statement S0, so in the ij iteration, we will be accessing the memory location at m of ij. Similarly, for the read operation, the iteration remains same, ij. For iteration ij, we are accessing the memory location m of ij minus 1, right? So using, and then we have the input schedule, which is the sequential schedule we have. So for our analysis, we completely ignore the parallel constructs first, and then bring in the parallelism later on for race detection. So here we have the sequential schedule, that is input schedule for this program, and then using this we compute the dependencies in the polyhedral framework. There's a specific algorithm to compute, and we have used the Poly's dependence analyzer for that. And so they basically compute these dependencies from this iteration domain scheduling systems. So these dependencies are valid only within this iteration domain, right? So this will limit these sets or the access maps or the dependence maps in this case, right? So this is the main modeling of the programs, and with this we go ahead with the race detection, right? So I have not added the algorithm and all. I have some examples to show how pictorially we can see the dependencies or violation of dependencies, right? So taking the same example here, the dependencies can be plotted as shown in figure 15. So we have a two-dimensional iteration space where I dimension is on the horizontal axis and j dimension is on the vertical axis. So if we plot these dependencies as we have shown calculated before, we will get a the red arrows as highlighted here, and each arrow represents one dependence. Okay, each dependence should be preserved by the program. If it is a transformation, they also need to preserve these dependencies. Even if it is a parallelization, still they need to preserve the dependencies, right? So how do we check the violation of this dependencies is that we take projections of this, right? So if we take the projection, it means if we remove the I dimension from picture, what we will have is that red dots. Are you able to see them? I hope so. So on the I dimension, we will have the projections, which is just the image of the dependencies. And here in this particular example, the projection on I dimension will leave us with like zero magnitude projections, right? So that means this particular dimension is parallel. We can, if we parallelize this dimension, then we will preserve the dependencies. But if we take the projection on the j dimension, if we remove the I dimension from picture, what we will left behind are unit magnitude projections. Okay? That means if we parallelize the j dimension, there will be dependence from two consecutive iterations in the j dimension, and that will violate the dependencies. And this is how we detect data races in the program. So if we parallelize the example in listing 25 in the inner dimension, then there will be definitely data races in at runtime, right? So this is the gist of detecting races in the program in the framework. So if you have any questions, you can I hope if then we can go ahead with the results and show some numbers that we have. All right. So like we use 3 different benchmarks for this work, and yeah, so out of this, one of them we have created and this is called data response program. So this is a contribution that is part of this work, and we have also used this data response in C++ and then Openmp Is version 2. So these are some common data response benchmarks that have been used in the literature, and we used 2 Intel Xeon processors for this, and which had total 72 threads, and we use LLOV for our implementation. So then we could compare our work with the state of the art, like the best tools that we have are Halbrine. I think most of you will be aware of Halbrine project. And Halbrine is a risk detection tool in Valgrind, and Valgrind DRD is another tool in the same infrastructure. LLVM has its own tool called TSEN, and Archer is another tool which is part of, now it's part of LLVM, but previously it was not. And yeah, it builds on top of TSEN. But Archer is another tool, and then Sword. Sword is one more risk detection tool which targets Openmp. Right. So among these, the first 3 are basically they target pthread based programs for risk detection. Since Openmp internally uses pthreads, so, like they also, these 3 also can detect data races in Openmp programs, but they provide false positives because they do not have information regarding the Openmp like high level semantic. And Archer and Sword are specific to Openmp. So for the first benchmark, data response, there were like 116 kernels, and like the coverage of our tool is not that great, but out of them it could detect maximum like a reasonable amount of true positives, but maximum number of true negative cases. So basically it could certify that 36 kernels in out of this 116 are data race free. So here the base numbers are highlighted in red as 57. So TSEN could detect maximum number of data races. Similarly, so since this coverage is not uniform, here we show the common 61 kernels that could be analyzed by all the 6 tools. Here all of them are able to detect same number of true positives, and Sword could detect maximum number of true negative cases. And yeah, so LLOV performs quite well in terms in this, like comparable to other tools. If we see the performance metrics like precision, recall, and accuracy, we are actually comparable to the other tools like Sword. Here is the best performer. Here the second best numbers are in bold. So you can see LLOV is having the numbers in all of the numbers in the range of 90s. Right, so this is for the whole data race benchmark, 116 kernels, and these numbers are for the common 61 kernels. So these numbers are a little bit, I mean, since if we go back, the coverage of Sword is less and the coverage of LLOV is less. So maybe, yeah, like they will have, Sword and LLOV will definitely have an advantage over the others, because once we have more coverage, this precision metrics tend to reduce. Okay, and so the best part of the work is in terms of the execution time. Here in this figure, we have shown the execution time taken by different threads, different tools. So as we can see, so the dotted line represents LLOV. Here we have, like, for the data expense version 1.2, it takes just 44 seconds to complete its analysis. And one more important thing is, like, the other tools are dynamic tools. Unfortunately, there were no static tools available. Open source or freely available tools, they were not available to compare against. And the state-of-the-art tools were all dynamic analysis tools. So for dynamic analysis tools, we had to run them multiple times, and we had to vary the number of threads as well, because for some combination of the threads, some data races were not triggered. Like, we will not be able to detect data races for some particular examples in the data race benchmark. For that, we have to increase the number of threads and repeat the experiment. So you can see that the execution time of the other tools are, like, quite high. Here, I think SWORD takes maximum amount of time. And this is also because there was a performance penalty for compilation timeout. So we have kept a timeout of 500 seconds for maybe 300, I don't remember. I think 500 seconds for both compilation timeout as well as execution time. So this tool SWORD was giving timeout for many of the kernels. Otherwise, yeah, so the second best performer was Archer, and Hellgrind was third, as shown by the green line. Right. So if we show the same plot for common 61 kernels, LLV performs even better. So it could detect in just 4.3 seconds, and other tools, the pattern is similar for all the other tools. Here, if we look at the plot for SWORD, so SWORD performs much better now because the performance penalties are removed, and SWORD actually performs third best in this, as highlighted by the blue line, and Archer performs best as well. Okay, so there was the next benchmark, which is commonly used in data race detection, which is Openmp Is. Here, there were many recursive programs, and the programs that were shown to, like, they were demonstrative of the power of Openmp constructs, but unfortunately they had some bugs in it. And so it is very difficult when we have a recursive program to determine or infer anything at static time. So LLOV could not perform much better here. We could detect like two positive cases, and it generated a lot of false positive. So these false positive numbers were basically because of two-dimensional arrays. Two-dimensional arrays represented by a double pointer. So that was a big bottleneck for us, because we could not figure out, like, the polyhedral framework could not figure out if that particular memory access, it could not basically delinearize it, and there were data races. Like, we had to produce, like, conservative results for it. Yeah, in terms of compile time, here also it's much better than others. It's like 5 seconds and thousands of seconds, so it's orders of magnitude faster than others. It's a very big plus point if you want to quickly have a say on, like, analyze your program quickly and see if there are any issues. You can run LLOV and start fixing the bugs readily, while the other tools will have to start the process and wait. The turnaround time becomes very large. You have to wait for the program to finish and see what other race is reported by the tool. So the third benchmark that we used was data response Fortran. This one, like, there was no Openmp Fortran benchmark available, so we have created this, and it is a translation of the C++ version of the data race benchmark. Out of the 116s, 92 we converted manually. Some others were, like, auto-generated by tools like tiled version of matrix multiplication and the other poly bench kernels. Okay, and this work is also available for free in GitHub. Yeah, so in this benchmark, we could detect only 3 tools could detect data erasure. So other tools like Archer and Sword, I think they even decent. So here, like this is just to demonstrate that the LLOV works for Fortran code as well, and there were a lot of differences in the generated IR from Fortran, and it was not same as the IR generated by Clang. I think now efforts are being put into having a common Openmp IR generator or common intermediate IR or lowering framework in LLVM, and I think that will eventually reduce the effort for us to like specialize our tool for flying front end. So yeah, so that brings to the conclusion that we have designed and developed a static analysis tool which was for data erasure detection, which was not available. So even though OpenMP is there for quite some time, there are not many tools that can detect data erasures readily and quickly. So enough, but there are, even though there are dynamic tools which gives which are production ready, I think they give quite good results. There was a need for static analysis tools which can give you quick feedback or quick analysis of your program. And if you want to try out the tool, you can go to the link as shown, which is on GitHub, and there's a blog post on it where we have specified how you can use it for C, C++ and Fortran, and how you can run from Clang and how you can run from using the optimizer OPT. And we are planning to open source this work. After, like, we are working on extension of this work, so I think we will sourcing this work soon. And yeah, so that brings to the conclusion of this talk. If you have any questions, you can ask, and or maybe I'll go back to the slide or present slide that I have talked. Yeah. So if you have any questions there, or if you have any questions regarding the LLOV, we can ask. We can go for this vectorization legality and parallelization legality.
Hi, Utpal. Thanks for the talk. I have just two quick questions.
Yeah.
So the first one is in the Fortran benchmark, there were just 3 candidates, right? So is there a reason why thread sanitizer was not able to run on Fortran benchmark?
I think Thyssen, where was it? This one, right?
Yes.
Yeah. So I think this for Thyssen we need instrumentation, right? So I am not sure if the instrumentation phase was available for, like, we might have tried. I did try it, but
Okay.
yeah, I maybe I was not able to like figure out. I don't know, or they did not have support at that time. Maybe they have added support for it later. I'm not sure about it.
Okay. I like, even I'm not sure. Like, I don't have much idea about the thread sanitizer, but yeah, I was just thinking that as you said that it instrument things, and I guess as you said that the IR generated for Fortran was comparably different that of C++. Maybe they may not be instrumenting it. Yeah, it makes sense. Okay. So yes.
Yes. Go ahead.
Yeah, I have one more question. You were using alias analysis results, right? for
Yes.
Fortran as well. So, do you think when type-based alias analysis will be supported for Fortran? I guess there are some attempts for that. Will it impact, like, will it help LLOV in some way?
Yeah, I think any improvement to the like the alias analyzer will help us. But I think specifically we only use modref analysis, so I'm
Okay.
not sure if like type-based alias analyzer will directly improve us. But like
Mhm.
indirectly they will improve the dependence analyzer. So yeah, ultimately they will they will have a good impact on LLOP. So I think alias analysis is indispensable. It must be like it should be used everywhere, and it is used everywhere. So any improvement to alias analysis will definitely help us for CCP.
Oh, wow, wow, that's great. Yeah, I guess I was not aware that. So yeah, I'm not sure whether we can use type-based alias analysis result for mod def info. I'm not sure, but yeah, it makes sense what you said. Yeah, thank you.
Yeah. Sure. Yeah. Any other questions?
We have a question on chat. Let me
Should I go
try.
or?
Oh no, no, no. I'll read it for you. It's fine. Fahad is asking, are there some hybrid static plus dynamic analysis tools for data risk detection?
Yes. Yeah. So Archer claims to be static plus dynamic. Initially, they started with static plus dynamic. Eventually, they dropped the static part. I think they use poly for like detecting that which portion of the code is parallel. We don't like what Archer does is like yeah, generally what TSEN does is it instruments the memory accesses, right, for violation of this happens before relations at runtime. And what Archer does is it improves TSEN. So it says that you do not need to instrument all the code. You just instrument the parallel code, right? So what Archer was designed is for like first blacklist the sequential code and the code that is like parallel. Like we know that the code will always be parallel, but if there's a section of code for which we cannot comment anything at static time, then instrument them and ask the TSEN tool to see if there's a data is runtime. So Archer was developed keeping in mind that we first use a static analysis. But right now, I think they are using some callback functions, which is there's something called Openmp library or interface in Openmp, recent version of Openmp. So they use these callbacks to like I think annotate like or instrument some of the code, not all sections of the code, that reduces the search phase or instrumentation phase of the TSEN tool. So it so if we go back to yes, can you see this figure 20? We have the time taken of Archer is highlighted by this magenta line, I think. Yeah. Then after that we have this orange line highlighted by TSEN. So what Archer does is it improves the time or time complexity of TSEN. So you can see that they are going side by side. Yeah, to answer your question, this was the tool Archer that aimed it, but I think right now they are not doing that in the version 2 of their tool. And I think we have plans to achieve something similar because TSEN is part of LLVM, and maybe we can try. Like we know that some section of the program are race free for sure. Then we can say that okay, this program is data race free, and for some section of the program, we can say that this part is definitely having a data risk. But what if there are cases where the dependence analyzer is not sure, where the dependence is confused? So maybe what we can do is tell the programmer that, okay, we instrumented this, please run your program and see if there are any dependence on the particular section of code. So that instrumentation will reduce the search space or the instrumentation space of DSEN, but it will improve the overall accuracy plus coverage of LLOV. Yeah, it's a nice question. I think we have plans for that. Yeah, am I audible?
Oh, yes.
Okay, sorry.
Yeah, so yeah, Fahad says thanks, sounds great, and thanks, yeah, on the chat.
Okay, okay. Nice. So maybe I can show you some examples maybe. So
Yeah, sure.
I'll ask. Okay. So yeah, is my screen visible to everyone?
Yes, it's visible to me.
Okay. So it's a quick question to everyone. Can you tell me where are the data races? Like at which line these are their data races? So we have a parallel construct at line 7, and then we have multiple for construct within it. There are four OpenMP work sharing constructs within it, and there will be data races for some of them. Can anyone tell me where the data races will be? Anyone? Just give it a try. Like maybe we can just discuss because then only we will learn.
So the first three has data races because there is dependence between the previous. No, I think the first and the third one because the trace for J the A of ij depends on the previous iteration of A of j minus 1. But for A of j, ij and A of I minus 1 and j, yeah, I think j can be run in
Yeah.
you can run j in parallel but stop on the next iteration of j.
Okay.
Right?
Yeah, good understanding. Yeah, like we can parallelize J. Yes. And anything, any more insight?
I think that's all I have. So this pragma of OMP4 will parallelize only the I iteration, right? Not J.
Yes,
Or
yes.
both. Okay. Okay.
Yeah. So there's a construct called collapse. So
Okay.
if we say collapse 2, that means now both the iterations, both the groups will be like divided among the threads. So since there are no there is no collapse clause, so here in this case only the outer loop will be divided among the threads. So the work sharing will happen on the outer dimension.
Okay.
Right?
Yeah.
Okay, so let us just analyze these four
And in that
examples.
case, the only second one has the data raise, right? Because for
Yeah,
every
precisely. So very good, very good. So here I'll just explain for others. In this first example, what we have is we have two loops and a work sharing construct outside has pragma OMP4. this work sharing construct will say that the first loop should be divided among the threads. So how many threads are there, or how many threads that are participating in this parallel construct will share this construct at line number 10. This follow. So if we look at the dependencies, we have a dependence from ij to ij minus 1. Here in the ith dimension, we are basically not changing anything. So if you see that any thread that is getting a particular value of I, it will write and read to the same row of the memory. Okay, right? So if the first thread gets I equal to 1, so first thread will write to all the i's, all the same i's. There is no change of that, and it also is reading from the same I. So no two threads will read and write to a common row. So all the threads will write to different rows. Hence, there will not be any data race for the first example. So the same same explanation goes to the last one. So the first one and third one is same, I think. Right? First, yeah, these examples are same, and for the last one, it is also the same, right? So the explanation is same, but for the second loop, what we have is that some like if we assign different i's to different threads, that means no two threads will get the same I. Then, even though all the threads are writing to different i's, but they will be reading to different. They might be reading from a memory location that is written by someone else. That means, suppose thread 1 gets iteration 1, thread 2 gets iteration 2. Now, the memory location or the row that is assigned to thread 1, that means A of 1 and J varies from 1 to n. So that row, while thread 1 is writing, thread 2 might be trying to read because of this I minus 1 J operation. Right? So because of that, we call this dependence is carried by the outer dimension. Whenever there is a dependence that is carried by a particular dimension, and that dimension itself is parallelized, right? So there will be data race. This, I think, if I show you, so if I run this example, this one is not that one. Yeah, this one. Is it visible? No. Is it visible? 1.11 please.
Yes.
Yes.
Yeah. Okay. Thank you. So if we execute this, we will have we will generate some race warnings like this segment of code is data race free. So this we can do it statically because we can model the program precisely from this line number to that line number. So in this example, basically, if we go to line number 24, which is the last loop, so like this is in reverse order because LLVM keeps the loops in reverse order. Yeah, so here sometimes what happens, the polyhedral analyzer does not preserve the memory locations. So here in this example, I think the loop locations were not preserved properly. Like so, there will be a different representation for poly, and poly will there's something called scope. So poly will work on it, and we will have memory accesses, and so each memory accesses will be annotated with these locations, like so that we can know which memory accesses specific to which location in the high level language. There's some issue with that for some programs. So like, then we just saw that this pragma is parallel basically. In this example, this code is parallel, there is no data race. So we can then state that this region is data race free. Similarly for 19, which is this third for loop, and then we have a data race detected for line number 17. which is this one. So we caught this data race here, violation of this data race. And yeah, so this can be like, it is very quick, as you can see, like instantly you can get this information, and you do not need to, like, this is the advantage of static analysis. You do not need to run it and then see the logs and infer what are the issues. But having said that, static analysis will have limitations because we cannot infer everything at compile time itself. So just one more example that I wanted to show is here. So this one I think I showed you in the paper, right? So there's a no wait clause, right? So this no wait clause will make sure that there is a data race from line 72 to line 75, right? So if we run, yeah, this one. So once it says that this section is data is free, so that means if we consider only this part, that is data is free, but there is a data race from line 12 to line not 12, sorry, line 72 to line 75, right? So this 72 to 75 at column 30. So this information can be captured by the tool, and it is quite fast. And if you want to experiment, I think we have yeah, so we have a blog post here where we have shown the examples and then comparison, and I think there's a link to GitHub at last. Okay. So if you want to try out, you can go to this tool. This is the tool. It is freely available. Source code is not open source yet. And if you want to see the, what do we call, if you want to compare with these numbers, you can actually download this Docker container and run the experiments and see for yourself. Reproduce the numbers. And yeah, we have detailed like these things, how you can run the different for C++ from Clang and from OPT, and then for Fortran code as well. And if you want to see the Fortran benchmark, this is open source. So there are these are Fortran kernels. They're like I think, yeah, there are 96 kernels, I think, 92, I think. Yeah. You can try out this if you want to work on Openmp. And if you want to contribute, then let me know. I think we can see what improvements we can bring. Like there are many that we have thought of, and I'm working on some. And so if you want to work or collaborate, please let me know. I think I'm open for any contribution, and you can reach me in my email, cs14mtech11017. So I think that's all I will have. All I have to say today. Thank you.
Thanks, Utpal. Thanks for the talk. It was really interesting. It was very interesting because statically finding it is difficult, and the numbers that you shown, they were just amazing.
I think like the biggest problem with static analysis is that you like you have to assume many things. So like that, like it's indirect. Like maybe when we use the dependency analyzer in turn assumes many things. Then when we use alias analyzer, we use many things. So yeah, like still we cannot provide a complete solution as such, but I mean we are trying. So there are, I think I have shown you comparison table. So like LLOV it does not cover many of these pragmas. Still, the coverage is quite good. Other tools, I think they cover a lot. Archer version 2 covers many of these pragmas. So I'm not sure about these themes. I think they have provided support for them as well. I'll have to see an update. Yeah, so we are working on providing support for more and more number of pragmas. And yeah, I think that will improve the coverage as well.
Yes. I guess we have a text on chat from Pratik. Pratik, would you like to unmute yourself, or I can read this on your behalf?
Hello, am I audible?
Oh yes, hi Pratik.
Thank you for the session, and I'm new to this LLVM, and I'm a contributor at Poly, and not a frequent contributor, but I'm trying to prepare myself for GSOC as a student, and this talk was little above my head, some terms were new to me, so it went above my head. So sorry,
It's fine.
and it was
It,
nice.
Yeah, thank you. Yeah, I think like the main aim is like we teach each other and we improve the systems proved in India. That is, I think that should be the main purpose. And I think I will be willing to help you if you need any help or do some amount of code. I think Rishabh can also help you. Then, like lot of experience, I guess. Yeah, so if you want us to review your proposals, if you write, so I didn't ask, did you like, are you applying for GSOC? I think it is application period will start soon. I'm not sure.
Yeah, no. Actually, the last date is 13. So I'm making the proposal right now. So
Okay. So yeah, so I was going there. So if you have a proposal ready and if you want us to review, like you can, if you don't mind sharing with us, you can definitely
yeah,
send us.
sure. Thank you.